Hello everyone, this is Nisita. Today I'll be talking about homomorphic encryption, securing data in news. This is an exciting area because it redefines how we protect privacy while still making full use of data. And this is particularly important for India's fast growing digital ecosystem, where we are generating petabytes of sensitive information every single day. And over the next few minutes, I'll take you on a journey why traditional methods of encryption are no longer enough, what homomorphic encryption actually is, how it has evolved over the years, and why it's critical for our future. But before we dive into homomorphic encryption, let's first understand what's wrong with the encryption we use today. Encryption is something we already rely on daily. Think about WhatsApp messages, online banking, or Aadhaar system. All of them use encryption. Now, encryption works really well in two cases. When data is stored, like files sitting safely on a hard drive, when data is in transit, like sending it over the internet. But here's the problem. When you actually need to use the data, whether for analytics, machine learning, or even basic arithmetic operations, the data must be decrypted first. And that moment of decryption is where vulnerabilities appear. During this short window, attackers, malicious insiders, or even a misconfigured server could expose the raw sensitive data. For example, in healthcare, hospitals often upload patient records to the cloud for AI analysis. Encryption is stripped away while the AI processes the data. At that exact stage, the sensitive details like a patient's blood pressure, medical history, or test results become vulnerable. So the big question is, how do we ensure data remains protected not just at rest or in transit, but also while it's being used? And that's exactly where homomorphic encryption comes into play. Homomorphic encryption, or HE for short, is the solution to this problem. Think of it like a locked box. Normally, if you want to do something with what's inside, you would have to open the box, exposing what's inside. But homomorphic encryption is different. It lets you perform operations directly on the locked box. Shake it, stack it, even combine it with another locked box, all without ever opening it. Only at the very end, when the computation is complete, you unlock the box. And when you do, you get the same final result as if you had worked directly on the raw data. This means computations can be performed without exposing any sensitive information. So, in simple terms, homomorphic encryption allows computations on encrypted data while keeping the data private. That's powerful because it solves the exact weakness of traditional encryption. To understand it better, let's look at the different types of homomorphic encryption that exist. There are three main types of homomorphic encryption, each with increasing strength. Partially homomorphic encryption. Unlimited operations, but only one type, either addition or multiplication. Example, RSA supports multiplication. Useful but limited since we usually need more than one kind of operation. Somewhat homomorphic encryption supports both addition and multiplication, but only a limited number of times. The limitation comes from something called noise. As more operations are performed, the ciphertext gets noisy and eventually cannot be decrypted correctly. Fully homomorphic encryption, the holy grail, supports unlimited additions and multiplications. You can run entire programs on encrypted data while training a machine learning model without decrypting anything. So, FHE essentially means we can have privacy and full functionality at the same time. Sounds a little abstract, right? Let's bring it down to earth with a simple example. Let's take a very basic math example. Suppose I encrypt the numbers 5 and 3. To us, they look like random, unreadable gibberish. But the magic is this: I can still add them together while they're encrypted. While I decrypt the result at the very end, I get 8, which is exactly what I would have gotten if I had just added the numbers normally. Now let me show you this idea in action with a real Python demo using the PyFill library, one of the libraries for homomorphic encryption. So we set up the encryption scheme. We encrypt some patient data, in this case, blood pressure readings 120, 130, and 140. Even while encrypted, we compute the average of these numbers. Finally, we decrypt the result. So the output looks like encrypted values looks like gibberish. For example, some random unreadable form. Each one looks completely random. That's the security. Nobody can figure out the actual number. But when we decrypt the final result, the system gives us 130. Notice how the system was able to calculate average without ever decrypting the sensitive patient values in between. This is exactly why homomorphic encryption is so powerful. You can analyze encrypted health data, financial data, or any private data set and still get correct results, all without exposing the raw data at any stage. Now that we understood how it works in principle, let's look at how this technology evolved and what algorithm makes it possible. The journey of homomorphic encryption has been decades in the making. 1978 RSA. The story begins with RSA. It had multiplicative homomorphism, meaning you could multiply encrypted values, limited but a big step. 1999 failure crypto system. This added additive homomorphism, allowing encrypted sums. Now you could choose between addition or multiplication. 2009, Craig Gentry, a major breakthrough. Gentry proposed the first fully homomorphic encryption. For the first time, we had unlimited addition and multiplication on ciphertext, but it was painfully slow. Hours to do a single calculation. Still, this was proof it was possible. 2016, Microsoft Seal made HE more practical. Seal implemented BFB scheme for exact integer operations, finance, banking, etc. CKKS scheme for approximate arithmetic in AI and ML. 2017, more libraries emerged. IBM HeLib for experiments, Google TFHE for fast bit level computations. Today, advanced frameworks like Palisade and OpenFHE integrate multiple schemes. They work with Python, TensorFlow, and PyTorch, meaning even data scientists can use HE without being cryptographers. Real world examples. Healthcare. Microsoft Seal lets hospitals analyze encrypted medical images for AI training while keeping data private. Finance. IBM HeLib enables encrypted fraud detection on transaction data. So, from RSA in the 1970s to today's framework, he has evolved from theory to proof to usable tools, slowly making their way into industries. Now, let's bring into closer to home. Why does this matter for India in particular? India has one of the largest digital ecosystems in the world. Think about Aadhaar, UPI, e-commerce platforms, telemedicine apps, all of them are generating and processing sensitive personal data. This is both an opportunity and a huge privacy risk. Example, healthcare. Hospitals can collaborate to train AI models on patient records stored in different cities, all while keeping the raw records encrypted. Finance. Banks can detect fraud in encrypted transaction logs, protecting customer privacy. Retail. Businesses can analyze customer behavior securely without exposing individual purchase histories. For a data rich country like India, homomorphic encryption is a perfect fit. It balances innovation and privacy, allowing growth without compromising trust. But like any new technology, it comes with challenges. The biggest challenge, performance. Fully homomorphic encryption is computationally heavy. Running on encrypted data is much slower than running on plain data, but progress is being made. Hardware accelerators like GPUs help AI. Dedicated chips are being designed for heat. Algorithmic optimizations reducing overhead, industry adoption, Companies like IBM, Microsoft, and the open source groups are actively improving HE. So while FHE started off as practically slow, it's moving towards practical usability. So what's next? Let's look at research direction. Research is focusing on four main areas: efficiency improvement, faster schemes, lower latency; scalability, handling massive data sets like in national health records; hybrid approaches, combining HE with different secure multi-party computation or differential privacy; application specific optimization, tailoring HE for finance, healthcare, IoT instead of generic solutions. The idea is not just to make HE faster, but also practical for real industries. So, what does all of this mean for the future of privacy? The future will be privacy first. Zero trust architecture. Data encrypted from creation to deletion. Federated learning. AI models trained across multiple institutions without sharing raw data. Privacy preserving cloud computing. Companies and even governments collaborating securely without data leaks. This is where homomorphic encryption fits perfectly as the backbone of secure, collaborative, and trustworthy digital system. Finally, let's wrap up with the key takeaway. To conclude, homomorphic encryption allows us to use data without exposing it. It unlocks innovation in healthcare, finance, and AI while still protecting privacy. The future of digital security will be secure, collaborative, and privacy first, and homomorphic encryption will be one of the key driving forces behind that transformation. Thank you.